So, welcome everyone to third lecture, ELEC1207, and today we're going to cover nodal analysis in its different shapes and forms. So we did mesh analysis last week. Nodal analysis is the same thing but slightly different. It's just another technique that you can use for analysing linear circuits. So, another summary, similar to mesh analysis, but nodal analysis can be used to analyse any circuit, not just planar ones. So planar ones, remember, were ones where you could draw them on a flat surface with no overlaps. These are any circuits at all. So nodal analysis is the method of choice for circuits having fewer nodes than meshes. But you should be getting the idea by now that in fact the number of nodes and meshes in a circuit is not completely fixed, because you can start to use these various transformations, Norton and Thevenin for example, to change the form of circuits in terms of how they're displayed rather than functionality. Functionality stays the same. So you can convert most circuits into other forms using the various network transform theorems that we've been talked about, and a few others that we will talk about going forward. So basically you can either choose nodal or mesh for any circuit, as long as you can convert that circuit into a form that you're happy with. So this one works by applying Kirchhoff's current law to the n nodes of the circuit, resulting in n-1 simultaneous equations. Why n-1? Because one node, as we shall see, is selected as a reference, and we know what that is because it's a fixed potential. So it could be ground, could be earth, could be anything really. It's not. It's just definitions. And then you get your equations, your n-1 simultaneous equations, and you then solve them by a method of your choice, potentially Gaussian elimination, but if you've got MATLAB, maybe something like that. But it's most easily applied to circuits with current sources only, no voltage sources. But again, you should understand that we can swap one for the other using a Norton and Thevenin theorems. So it's always easier with an example. So, example, circuit with a current source. So here's a current source, and here's another current source, and then there are a few resistors in this circuit. No voltage sources, you'll note. Procedure, as it says, it's better to work in conductances. Remember, conductances are 1 over resistance. It's going to happen anyway in the maths. We select a reference node, generally ground if defined, but it could be anything, and assign node voltages to all nodes, or variables to all nodes. And in this case we've identified our nodes as A, B and C, and just labelled them as such. And then we measure with respect to the reference, and in this case it will make sense to make C the reference, because everything seems to be measured with respect to that anyway. Apply KHCl to each node, summing the currents leaving. Remember, they all add up to 0, and what goes in must come out. Gather up all the terms for each node, write the matrix equation and solve it. So once we get to this point here, then we've seen it before and we should be okay. Right, so in our example we've chosen node C as the reference, and now we want to work out what's going on at node A and node B. So we want to look at the currents, sorry, very creaky chair, currents going into or out of A, and we add them all up. So node A, we've got 3 amps. So again, the current source is defined as being 3 amps in this direction, but if we define all currents leaving the node as being the ones we're interested in, then this current here must be -3 amps as defined by the direction of this arrow, plus 3 amps as defined by the direction of this arrow. This arrow wins because it's our definition for the node. So we've got -3. We're then going to have 0.5 VA, so I've converted these resistances into conductance. So 1 over 2 is 0.5, 1 over 4 is 0.25. So this one becomes 0.5 plus 0.5 VA. Okay, so we've got the current is the conductance times the voltage, so that's where we get that from. And then this one is the only interesting one in many ways, because remember, we're looking at the voltage difference across this node, and the voltage difference as defined would be VA minus VB. Multiply that by the conductance, 1 over the resistance if you like, gives us the current as defined in this direction here. So we get 0.25 VA minus VB. They all equal 0, 3 currents leaving all add up to 0. And then we can just rewrite that. I've just rewritten that for clarity. I can't see a difference there. So sum the current leaving node A. Remember, current equals conductance times voltage. Then do the same for node B. So if we do that for node B, we get the same kind of equation, and we can start to see some similarities. So this one part here relates to the current. So we're on some other arrows that I haven't drawn this way. So I've got an arrow going from B to A in this case. So that's an opposite to this one. We've got 6 amps leaving the source, and then we've got 0.25 VB, whatever VB is, that's the thing we're interested in, equals 0. So all we've done, to recap, is we've summed the currents leaving this node, we've summed the currents leaving this node. That gives us 2 equations for node A and node B. We gather the terms up, so we just simplify these two, and we end up with 0.75 VA minus 0.25 VB equals 3, and minus 0.25 VA plus 0.5 VB equals minus 6. So that these two here are just these two, just with the terms collected. So we can now make our matrix, which is easy enough. So we've got it in the form with VA, VB, VA, VB, and then we can just take out the coefficients. I just bung them into the coefficient matrix, and then we've got VA and VB, which is our vector of input variables, and the answers are 3 and 6, which are just coming from the equations. So that's the matrix equation that we need to solve. Again, we can start to look at it, helpful in sort of test or exam situations, or if you do loads of these things, to make sure you remember the chance of getting this matrix right. The conductance matrix is symmetrical about the major diagonal, so there's the major diagonal and its symmetry, this number is the same as this number. It's quite trivial with a 2 by 2 matrix. The terms on the major diagonal are all positive, and the terms off the major diagonal are all negative or 0. So it's the same as before in the mesh equation in many ways. So what we've done, you see, is we've massaged it into a form that we now understand, and we have some standard techniques for solving this form of equations. The fact that this represents a circuit is now irrelevant. We're just solving a mathematical problem. So if you know about how to form these matrices, circuits like this can very quickly be put into matrix form almost by inspection. The right hand side of the matrix equation is the sum of all the current sources connected to the node, positive if currents go into the node. So we've got a 3 here, and we've got a 6 here, which is the 3 and the 6 over here, and just check the directions. The positive major diagonal terms represent the sum of all conductances connected to a given node. So conductances, remember, not resistances. So this one is 0.25 and this one is 0.5, so we end up with 0.75, and that's that there. Likewise, we've got 0.25 there and 0.25 there. That adds to give us 5, and this is the one that's associated with both of these nodes, so that will be the one that goes in the diagonal. Okay, it's just to help you a little bit. So then we can solve these equations. Again, we can do that by Gaussian elimination if we want to. Start by multiplying row 1 by 4. So this row here, multiply that by 4. That just gets us to some nice whole numbers here. So the 3, the minus 1, and the 12. And then get to the right point. Multiply the bottom row by 12 in this case. Now, the idea there is to try and get us to the same number in these 2 points here, and then we can either add or subtract them depending on the value of this sign here. Add the 2 new rows to make a new row 12, and the idea there is that we can add these 2 together to make a new one that's got a 0 in the bottom. So we've got the 0 here now, and this would now be in echelon form. So just remember to do the same to this side of the equation as well. So now it's easy to see that if we start to multiply this out, this will be 0 times VA and 5 times VB is equal to minus 60, and this will be 3 VA minus 1 VB is equal to 12. So in this case 0 times VA, so VA is not in this equation. 5 times VB equals minus 60, so VB obviously equals 12. Once we've got that, we can back substitute through. Right, let's get rid of me. You'd be bored of seeing me by now. Right, so having got VB, we can then create the new equation for the unknown VA, because we can put VB in here. So now we just multiply out 3 times VA minus 1 times minus 12 is 12 plus 12, and that's going to equal 12. So we can rearrange that to give us VA equals 0. So now we can go back and say, well, what does this mean practically now we've got these two voltages? So if we think about this, this means that there is 0 voltage across the 2 ohm resistor. And what does that tell us? Does it tell us anything at all, really? Well, what it tells us is if there's a component that's got no voltage over it, then no current can flow in it. So we could just remove that component and it wouldn't actually affect the operation of the circuit under those conditions only. Under different conditions, if we made this 4 amps, for example, then there may well be a voltage across here. But under these conditions, with 3 amps here and 6 amps here, this resistance with no volts across it might as well just not be there in the circuit. We could take it out and would have no impact on the operation of the circuit under those conditions. Okay, so that's just something to think about. Just analyse what the answer is when you get it. Right, as always, as we said at the end of the last lecture, do a sanity check. Always check your answers. So we take the original equation for node A and put the numbers back in and just make sure that we get some sensible numbers out. And the answers we put in work, they all come to 0, so the answer is right. It's very easy to check these things. Less easy to check when you've got a lot more equations involved, but for the purposes of tests and exams and things, always go back and check. And in fact, if you're building a circuit and you've done analysis like this, check it first, because it's much easier to change the calculation than it is to change the circuit later. Right, so that's basic nodal analysis. Now we'll have a look at nodal analysis with mixed sources. So that's a combination of current sources and voltage sources to try and make it a bit more general. Sometimes in the circuit we'll have mixed sources. So here we've got a current source, which we should be relatively happy about for a nodal analysis, and what we've introduced here a voltage source. And we haven't dealt with the voltage source before, but it's not that difficult to deal with. Right, so here is a voltage source E1 between V3, node V3, and ground. This is helpful as we know the voltage at E3 now. The only thing connecting to node 3 is this voltage source, so we got lucky in this particular circuit. We know the voltage at V3 is E1, whatever E1 happens to be. If we didn't know that, if it was a bit more complicated than that, we would have had a 3 unknown problem. Excuse me. We would have had V1, V2 and V3 to worry about, whether these are the node voltages in a 3-node system. But now, just by looking at it, we can say it's only a 2 unknown problem, V2 and V3. Oh, sorry, V2 and V1 that should be, because we know what V3 is. So yeah, it's a little mistake there. So again, we apply a node. Now node is a little bit more complicated. V1, it's got 4 currents leaving it now. They all add to 0. We've defined them leaving. So we should be getting the idea now. So we turn the resistances into conductances just for the ease of writing it. Otherwise we'd have to have 2 lines of text. So V1 minus V3 multiplied by G1 gives us this current here. V1 G2 gives us this one here. V1 minus V2 G3 gives us this one here, and then we've got minus I, because I is defined in this direction but the red arrow is defined leaving, so it becomes negative. And then for node 2 we've got V2 G4, which is this one over here. We've got V2 minus V1 G3, which is this one, so it's the opposite of this one. And we've got I again, and again the direction is in this case current goes into V2. The current is defined as leaving, so I1 is in fact in the positive direction this time. And for node 3, write the equation down for completeness. V3 equals E1. That's just the nodal analysis for this point here. There's nothing else going on in terms of the voltage. Right, so we gather the terms as before to get everything together. A little bit more complicated, but if you can just pull it all out, you end up creating the matrix equation. In this case, we've got G1 plus G2 plus G3 times V1 and G minus G3 times V2. So if you multiply this out, you'll get these equations. And G3 times V1 and G3 plus G4 times V2 equals minus I1. Okay, so it's been left as a little example for you. You should get a bit of pen and paper out. Take these node equations and see if you can construct this matrix equation. The solution then follows as before. You can solve this matrix however you like. You can do it by Gaussian elimination if you want. Okay, so let's put some numbers into it. Easier to work with numbers, much more specific. So we've defined conductance of 1, which is an impedance of resistance of 1. 0.5, so that's 2 ohms. 0.2, so that's 5 ohms. 0.75, can't do that in my head. But it's 1 over 0.75 in terms of resistance. 2 amps of current, 5 volts there. What are V1, V2 and V3 in this circuit? Okay, so we know how to calculate or to develop the node equations. If you're not sure, you can drop back a couple of slides and have a look. Otherwise we can do it from first principles again, just write them down. V1 minus V3 G1, V1 G2, V1 minus V2 G3, and minus I for that node there, and likewise. So simplify that down, throw some numbers in. We can pick the numbers off the chart now. 2.25 V1 minus 0.5 V2 minus V3 equals 2. Same again for node 2. Develop the node equation, put the numbers in, simplify it down. Minus 0.5 plus 0.7 V2 equals minus 2. And for node 3, V3 equals 5. Because it's connected straight to this voltage source. Yeah, it can't be anything other than 5. Yeah, because this is a 5 volt source, it's a perfect source, it's going to make this 5 volts come hell or high water. Right, so we can construct a matrix equation from this. So we've got V1, V2, V3, V1 and V2 and V3. Plug that into our matrix equation and it comes out like this. So this is now a 3 by 3 matrix, although the third node here is actually quite a trivial solution, but we've done the full solution here. V1, V2, V3, and these are the right hand side that comes out of it. So we would normally have to do the Gaussian elimination to get it into echelon form, but the third line in this case is already in echelon form for us, which is quite helpful. We've got 2 noughts, 2 nought, 0, 0 and a 1, so we don't have to worry about this line. This is all great. What we need now to worry about is getting this one into a form where there's a 0 here. And then we should be ready to go with it. Right, so in this case, and there are loads of different ways of doing this. This is just one. I mean, you can probably do it in one step if you can work it through yourself. Multiply row 2 by 4.5 to give us this now. So, and now we can see that these two numbers are the same in magnitude, even if not polarity. So we can add these two rows together, and that will give us a naught at this point here. And we will have a new equation that's then in echelon form. And here we are the steps if you want to work it through. Make a new row by adding rows 1 and 2, and we end up with this new equation. And now it's in echelon form, so remember it's increasing numbers of noughts, and we can do back substitution to get to our answers. So we can see, if we multiply this out, we've got 0v1 times 0v2 and 1v3 is going to equal to 5. Excuse me. So that's helpful enough. So we can substitute 5 into here, and then we can just substitute back in for this row here. We get 2.65 V2 minus V3 equals minus 7, which is easy enough to work out for V2, which gives us that, and then we can just substitute back into row 1 with the known answers for V2 and V3 that we've got now, allowing us to calculate V1, which comes out 2.94. At this point, for the purposes of academic exercise and for the practice of using the simulator, you can check by using the simulator that you've got your own answer. So if you want lots more examples of these, you can just draw your own circuits, put the currents in, work it out by nodal, mesh, or whatever analysis you want, and then to check you've got the right answers, put it into the simulator and check that everything lines up. If you get different answers, then you've either simulated it wrong or you've calculated it wrong, and it's up to you to then work out which one it is. So in this case, we've put it into the simulator. We've drawn, this is LT Spice. We can draw it in the simulator. We put the values of 1 over 0.75 is actually 1.33, and then 2 there, 5 there. Current source. So you define you can pick out the current source from LT Spice's list of variables, list of components. A voltage source, set it at 5, and then you run something called an operating point analysis. So you just select from a drop down menu operating point analysis and then run the simulation, and it will drop this .op onto the text, which is telling you it's configured for an operating point analysis. And an operating point analysis just works out the steady state conditions within the circuit. And then it will either pull up a little chart telling you what's going on, voltages at the various different nodes. You then have to wave your mouse over the different nodes and it will pop up and tell you what node it is it's talking about. So in this case, for node 1 is 2.94 volts, which is what we calculated. 3 is 5, so that would be that node there, and minus 0.754 volts for the other one. It also allows you to delve in and look at the currents in the simulator as well. So it's telling you the current through R4, current through R3, current through R2, that kind of thing. Once you've run an operating point simulation, if you then wave your mouse in LT Spice over the component in question, it will also pop up and tell you what the current is through those devices just by pointing at it. So it's actually very powerful, and I do recommend that you start practicing with LT Spice and some of these little circuits. Right, so that's how we deal with multiple sources. It's relatively straightforward. We just follow the rules again. The remaining thing that we need to look at is something called a supernode. So nodal analysis with supernodes is now what follows. Supernodes. So here's a circuit starting to get a little bit more complicated than the ones we've just looked at, but basically we can still see there are meshes and there are nodes, and so we should be able to still apply this analysis. The problem we have here is this circuit has a voltage source E2, which might not immediately look like a problem, but it is. Excuse me. So it's connected to two nodes, V1 and V2. Unfortunately, we don't know their potentials. In the previous case, we knew the potential of one node, it was at ground, and we knew the potential of the voltage source, and so we knew the potential of this node here. Now all we know is there's a difference in potential between these two nodes, but we don't know what the actual potentials actually are. All we know is that this node is going to be E2 bigger than this node. The problem is that the current through the voltage source is undefined. A voltage source only defines the voltage across it. It doesn't tell you what the current is coming through, and that's the beauty of them. They will give you whatever current you need to maintain that voltage, which is a bit of a problem if we want to work out what that current actually is. Right, so it says that the current through E2 could be anything, unlike if it was a resistor. It's well defined as a resistor, and it says go back to the definition of an ideal voltage source if this is not clear to you. We could define a new variable, I, which is the current going through here, but that just makes things a bit more complicated, as we would have four unknowns to solve for, V1, V2 and V3, and now this new one, I1. What we're going to do is introduce a bit of a shortcut. by introducing a thing called a supernode. And so a supernode, this is the supernode, it's the two nodes and the voltage source that we're a bit unsure about what the current is. So we would define this as a supernode. So a supernode is just a connection of two nodes, really. We then treat this supernode as if it was a single node. And this is allowed because if the total current leaving node 1 is 0 and the total current leaving node 2 is also 0, then the total current leaving the supernode must also be 0. So what effectively we do in sort of simple terms is we ignore it. We treat it almost like this voltage source isn't there. We can consider almost that these two are connected together, and that simplifies things a lot. And then later we just add in another step that puts this voltage source back in again. So it sounds confusing. We will just see how we do it with an example. But basically it's very simple. It's as simple as basic nodal analysis. The trick is just identifying there is a supernode and then knowing that you can deal with it as a supernode. So we apply KCL to sum the current leaving the supernode, and then we look within the supernode and write down the voltage source equation, which relates the value of the voltage source to the voltage between the two nodes to which it's connected, which is normally just the value of the voltage source. And we'll see how we do that in practice. It sounds complicated, it's actually very easy. Substitute the voltage source equation into the supernode equation and the other node equations, so and then we can solve it. Okay, sounds complicated, let's just see what we do. So we form a supernode of nodes 1 and 2. So we notice that this voltage source here is undefined, but it's current through it. We don't really know much about it. So we say that's our supernode. So what we're going to do then is sort of ignore this. And we're going to say, what's going on here? We've got this current source here, and it's current leaving, so this is negative. So we've got minus I1. We've got V1, G1 for a current leaving down here. We ignore this. Then we go over here and we say V2 G2 is leaving, and then we've got V2 minus V3 G3 going on over here, and we say that's naught. So we've treated this bit and this bit as a single node and sort of conveniently ignored this bit. Okay, so just take that as read for the moment, and then we go over here, node 3. Now we're happy with node 3. There's nothing clever going on or complicated going on here. We've got minus I2 because the current is leaving the node, so it's defined as minus I2. We've got V3 G4, which is the current going down here, and then we've got V3 minus V2 G3 for the current leaving this way. So it doesn't involve the supernode, this is just a normal node, and that's what we've got. And then we have to remember that we've got another equation that is the voltage source equation, which is the link between these two nodes, and it's just the E2. So V2 minus V1 is equal to E2. That's just the voltage difference between these two nodes, and it's defined by this voltage source, and that's all that is. E2 is fixed, it's a voltage source. So there's our set of equations that we need to solve. We should have the right number of equations for the right number of unknowns now. Oops, gone the wrong way. If you did it the long way, you would be doing this kind of thing. You'd say node 1, you've got minus I1, V1, G1, plus this unknown I, which we've had to define, equals naught. We do the same thing for node 2. We get minus I plus V2, G2 plus V2 minus V3, G3, which is what's going on at this node here, equals naught. And then we can combine these two equations and just substitute out for I, and we end up with our supernode equation, which is the same as the previous slide. So if you want to do it the long way, you can do it like that, but identifying there's a supernode just allows you to miss out some maths, which if you're anything like me, you'll get wrong. Right, so here are our three equations, all set up nicely. We can then use the voltage source equation to substitute for V2 in the supernode and node 3 equations. So we can just rearrange this to give us that V2 equals E2 minus V1 as an example. Substitute, and that brings it down, that gets rid of one equation, and that allows us to then only have a 2 by 2 matrix to worry about involving V1 and V3. We can just construct the matrix equation, a little bit more complicated on this side this time, but it's exactly the same rules, and then we can solve that normally. because it says by a method of your choice for solving simultaneous equations. So again, all we've done is massage this down into a form that we're happy with, that we know we've got tools to solve equations in this form. Whatever's in these columns doesn't matter, it's just a set of equations, and then we can solve them, and then it's all great. So another example. Analyze the following circuit and calculate the nodal voltages. So two things to note. The voltage at V4 is 50 volts. It's the only thing connected to that node that's got a source on it. It's 50. It's completely defined by the voltage source E1. There's no way that this point V4 can be anything other than 50 volts because it's connected to an ideal 50 volt source. There is a supernode between V2 and V3 because we've got a voltage source which will have a current through it, but we've no idea what that current is because we've no idea what's defining these voltages here. All we know is there's a difference of 5 between these two voltages. A difference, not their absolute numbers. So we know it's a supernode problem, and it looks complicated, but actually we can simplify it down because V4 effectively is already known. So I've written some working by hand because it takes too long to create nice notes for it. So nodes 2 and 3 make a supernode, as we've already established, these ones over here. So we'll just analyse for V2 and V3. So we've got V2 minus V1 over R2. So I haven't gone to conductances for this at the moment, but I will do in a minute. So that's V2 minus V1 over R2 is the current leaving the node in this route. We've got V2 over R3, which is the current leaving this one. We ignore the supernode, go to the other side. We've got V3 over R4, and then we've got a current leaving here of value minus 4, because the 4 is defined in the other direction as being positive, equals 0. Then you can rearrange that, and I've turned them into conductances now, so this R2 has turned into a conductance G2. It's the same, it's just a different way of writing it. Likewise G3 and G4 equals 0. We can put down the constraint equation or the node equation for this supernode here. We just know that it's going to be V3 minus V2, which is the difference across it, equals E2, which is 5 volts in this case. That's just what it is. And then we can create a substitution. You can either substitute for V3 or V2, doesn't matter. I've gone for V3, which is equal to E2 plus V2, just by rearranging this. Sub that into there, and that will get rid of one of the variables for us. For node 1, this one here, we've got V1 minus V4 over R5, current leaving that node that way. We've got a current leaving the node that way, V1 over R1, and we've got a current leaving that one, which is V1 minus V2 over R2, and that equals 0. Simplify that down. And for node 4, we know V4 equals 50 because that's the only thing connected to it. Can't be anything else. We then construct our matrix equation, and you can see that it's easy to make mistakes. I get the signs wrong quite regularly and subscripts wrong as well. But I have to go back and check, and then it's all sorted out. So V1G3 minus, and so on, I've got to read them out, equals 0. Another one equals 0, and V4 equals 50. We can turn that into a set of matrix equations because we've got it in the. We can separate out the V1s, the V2s, and then the V4s. Turn them into this coefficient matrix. Again, if you multiply this out, you'll find that it comes to this equation. And then we've got to turn this into echelon form. So we need to substitute in the real numbers and solve the matrix equations. Put in the real numbers. So there we are, some real numbers. Put them into the matrix, and now we've got a real problem to solve with just numbers, so we can work out to a numerical answer now. Bottom line is okay again because it was such a trivial node. We've got to do something about this middle row if we want to do the Gaussian elimination. In this case, multiply middle line by 0.325 over 0.2, so you're going to need a calculator for this. If you do that to all of those numbers in there, we end up with, importantly, these two the same, except for the difference of sign. Add the rows together. That then gives you a new middle row and we're into echelon form. You can see instantly then that V4 equals 50, but we knew that anyway. So if we wanted to, we could have reduced this down to a 2 by 2 matrix quite quickly. And then we do back substitution through having a calculator, knowing what V4 is, we can run it through the second equation and then finally to the third equation, and that gives us the answers. So V1 is 55.83 volts and V3 is 5 volts higher than that, 70.72. So hopefully you can start to see how we can start to solve these problems with just a relatively simple set of tools open to us. Again, it's sensible to simulate this, and then once again it comes out with the right answers, and it's the same. So it's a good way of checking, certainly while you're learning how to do this or worried about it. Right, so now we probably need to get back to mesh analysis, because we only looked at one type of source with mesh analysis. So we'll do the same again with mixed sources and super meshes for mesh analysis. You can imagine it's going to be very remarkably similar. Let's go backwards again. Right, so mesh analysis revisited. We previously looked at meshes with no current sources, only voltage. So let's look at one that's got a current source in it. So this one now has a current source, also has a voltage source, and we've got some meshes that have been defined in a clockwise direction. This circuit can easily be analysed because the mesh current from mesh 1 is equal to the current source. In this case, I1 is equal to I, just by inspection. Great. The 3-mesh problem therefore reduces to a 2-mesh problem, and we can compare this to a similar situation with node analysis. If we'd had a voltage source here, that would have told us that the voltage here was fixed because it was the only thing connected to the voltage source. So just by looking at these and applying a little bit of knowledge, we can maybe start to simplify things. So we know that I1 is equal to 1. So that's a useful substitution we could make if we wanted to. But let's do it formally. We've got current here. We can say that I1 equals 1. I1 equals I, in fact. For mesh 2, around here, we've got R2, I2 minus I1, R3, I2, which one's going on in this one here, and then R4, I2 minus I3. So it's a little bit more complicated than the last mesh we looked at, but we just apply the rules and off we go, and that all equals naught. Mesh 3, okay, so it's this term again, but the opposite to the previous equation, and then E. E is the voltage, that's what we're interested in, equals naught. And then if you start to simplify these two equations down, we've just got rid of I1, it's not important, doesn't appear anywhere else. We've got R2, R3, R4, I2, I3, and R4 and R4 here as well. So what we've done is we've actually substituted I1 for I in this equation here, and the I is appearing in this part of the matrix. But that's an implicit substitution. Hopefully by now you should be happy with those. But what has happened to R1? If we look at this matrix equation, there's no R1 in it. There's no R1 anywhere in here. R1 doesn't appear in this equation. Therefore, its value is irrelevant to this circuit. This is because the current source I has an undefined voltage across it. So we had that problem with the super mesh with the voltage source. It had an undefined current through it. This one's got an undefined voltage across it. So if you changed R1, the voltage across it would change because the current was constant. This current is constant, so the voltage here is almost irrelevant really, it's not affecting anything else. And the voltage across the current source would adjust itself accordingly to maintain the current through here, whatever is going on. But the current summing at the node, this node here, completely unaffected because it's currents we're interested in. Voltage over here could be whatever it likes, we don't really care. It's the currents that we're analysing in this sort of problem. Right, so you can do that. Put some numbers in for the resistors in the preceding circuit, calculate the currents. Then, that says then, not the, put it in the simulator and check that your answers are correct. So there's some interesting stuff to carry on with. So just quickly then to finish off, we can do super meshes. Here we've got a current source. We don't know the voltage across the current source because it's a current source and they have undefined voltages across them. So we cannot easily apply KVL to meshes 1 and 2 because of this unknown quantity in here. So likewise, as we did before, we could define another variable V, being the voltage across I, but that just gives us another equation we have to solve for. Not impossible, but maybe we can think of another way. So let's define a super mesh of meshes 1 and 2, and we effectively ignore the branch with the current source in it temporarily. So we're going to go round this mesh because we don't like the undefined thing, so we'll ignore it for as long as we can. So for the big mesh, minus E1, R1 I1 to do with this one, R3 I2 to do with that one. So remember, now we're interested in I2 as the mesh current in this part of the loop. It's I1 over here, so we have to make that change. R4 I2 minus I3, that's the one down here, equals 0. I3 R5 plus E2, got quite happy with the voltage sources. R4 I3 minus I2 is going on there, and that's a standard mesh. Okay, so we've ignored this bit for the time being, but we have to define I, this source here, in terms of the mesh currents, which we know to be I2 minus I1. That must be what's going on here. So now we've got a linking equation. So now we have three unknowns, I1, I2 and I3, and three equations describing them. So it can be solved, and we haven't had to worry about this unknown voltage V, and we don't care what it is either. So exactly the same as before, we just need to construct our matrix equation, which you can just go back to the previous slide, copy the numbers over and see how it goes. Slightly more complicated on this side, but it's still following the basic rules. It just comes from the previous equations, and unsurprisingly, well, it should be unsurprising now, R2 doesn't figure in the equation as it has no impact on the value of the current flowing through it. Okay, current through it is driven by this current source, and that's it. So it doesn't really matter what's going on in that resistor. It could be what it likes, and the equations have just recognised that and dropped it out for you. The maths don't lie. Okay, so we'll stop at that point, and we'll pick up next time on dependent sources, which is starting to get a bit more interesting then. Dependent sources lead us into all kinds of things like transistors and field effect transistors. So we'll stop at that point, and thank you for listening.